Okay, do you guys remember when we talked about frequency? Frequency being like angular speed, and we disregarded the word frequency. We used angular speed or omega for what frequency, meaning the revolutions per second. And we avoided the term frequency. We preferred to use the word angular speed. Well, we're taking that back now because we already talked about circular motion. Now we're talking about simple harmonic motion or vibrational motion. So frequency now is the number of cycles that an object completes when it's vibrating in a given amount of time. So instead of revs per second, we'll have we will have cycles per second. Okay, so frequency equals n number of cycles. Well, they're using n, I just use cycles. Over the time. So the unit is cycles per second, CPS, or cycle per second is also called a hertz. Okay, unit, we don't say cycles. We just do the number over seconds, which is weird. So I'm not going to worry about that. Okay, so here we go, right there. The unit would be hertz. So what is a cycle? Well, you have this something vibrating. Vibrational motion is called simple harmonic motion. Simple harmonic motion. Harmonic means repeating. Okay, also called periodic motion or oscillation. Okay, it's a back and forth motion of vibrating, or vibration. So a pendulum, think of a kid on a swing. A pendulum goes back and forth. Okay, this is one cycle going back and forth to the original position. Okay, so back and forth. Really, it's forth and back. I don't know why I say back and forth. One back and forth motion is equal to a cycle. One cycle. So if you put a ruler and pull it back and it goes back and forth, one back and forth motion is a cycle. Okay, here we have a block on a friction-free surface connected to a spring. Okay, so here's the spring when it's relaxed, and here's when it says maximum compression. And if you go down, that's where it's at its maximum extension. So we call this, where it's relaxed, the spring has no EPE. We call this position the equilibrium position. that is where the delta x, the displacement from the rest position or equilibrium position, is 0. So it's at the rest position. The maximum displacement, whether it's compression or extension from the equilibrium position, it's called amplitude. Okay, so there's a new term for you. Amplitude. Given the capital letter A, is the maximum displacement from the equilibrium position. Okay, so if I push this black all the way in, as shown in diagram 1, and released it, it would go back and forth. Where would one cycle be if you start at 1? It would be all the way back to the original position right here. So, let's call this position 2, 3, 4, 5, 6, 7, 8, and then 9. Okay, when you're fully compressed again. So that is one cycle. To go from 1, 2, 3, 4, 5, 6, back to equilibrium position, 7, 8, 9, back to the original squash position. That is one cycle. So going from 1 to 9 equals one cycle. How many amplitudes are you doing in a cycle? Okay, well, going from 1 to 3, you did one amplitude, right? And then going from 3 back to, 3 to 5 is another amplitude. Amplitude is the maximum displacement, right? And going from 5 back to the equilibrium position is yet another amplitude. And going from the equilibrium position back to the squash position is another amplitude. So the black is vibrating 4 amplitudes in its simple harmonic motion in one cycle. One cycle, for one cycle, the vibrating object, or the object in simple harmonic motion, travels 4 amplitudes. That's an important concept. I ask that, and people forget about that all the time. Okay, let's look at the energy aspects of simple harmonic motion or vibrational motion. Okay, you can see that at the amplitudes, let me highlight these. Okay, at the amplitudes, where's the other amplitude? Right here. Okay, at the amplitudes, you can see that the force, the restoring force, elastic force, is greatest. So let's point that out. And then let's compare it to equilibrium position. Okay, restoring force, the elastic force. Is maximum at the amplitudes or delta x max. But at the equilibrium position, when the block's at the equilibrium position, like right here, there's no force. So the elastic force is 0. Okay, so because F equals, okay, before I go into that, this thing right here, U, is AP term for US, is what we call EPE. They use U for potential energy, and then they put a little S for spring potential energy. We use EPE. So where is the EPE, which you know is K delta X squared over 2? Where is it maximum? Well, isn't it when the spring is most stretched out or most compressed with the biggest delta X? So the delta X is greatest, and we can look at this, F equals K delta X. Okay, delta X is greatest when the force is greatest, so I can fill that into right there. So because X is greatest at those spots, so is the elastic potential energy the greatest. And then it's 0 at equilibrium point because there's no delta X. If there's no delta X, there's no delta F. And there's no, that would happen at the equilibrium point. And then KE, well, the total mechanical energy is the KE plus the EPE. So the total mechanical energy is all EPE at the amplitudes. So EP is maximum at the amplitudes. But what about KE? K is kinetic energy, the energy in motion. Well, at the amplitudes, you're at rest because you have to turn around. So KE is 0 at the amplitudes, but KE is maximum. Let's look at it. Maximum at the equilibrium position. Okay, so you can see that. There's this back and forth, increasing, decreasing, increasing, decreasing between KE and EPE. When the KE is super big, the EPE is 0. So when the KE is smaller, the EP is bigger, etc. So they keep on, you can see by the heights of the bars in this energy bar graph on the right side, as the EPE shrinks, the KE builds until we have no EPE, all KE, and then the KE shrinks and that potential energy increases until we have no KE and maximum EPE. Then EPE starts to shrink and the KE builds, etc. and etc. repeating over and over. So these are concepts that you need to know, understand. And we could add a few things. Okay, so this is just explaining what I just went through with the spring. But force could also be the gravitational force. If it's like a pendulum, the force that swings it back is the x component of the weight. So there's a part of the weight that brings it back to the rest position, but when it's at the rest position, equilibrium position, there's no x component to, so that Fx, F is the gravity, the weight, so that x component of the weight will bring it back. But then at the equilibrium position, that Fx goes 0. So it's the same kind of idea, but the vector diagram is more complicated. So you don't really need Hooke's law unless you're using elastic potential energy. Now in the pendulum, it's not elastic potential energy, is GPE. It goes back and forth with the KE. Okay, so we'll talk about that later. So for a pendulum, it's gravitational potential energy. I should put that. Energy is continually being shifted between these two types, but the total energy is constant. So the mechanical energy always is going to equal the KE plus the PE, whether it's EPE or GPE. So this is ridiculously easy. The period is 4 seconds. What is the frequency? So frequency is 1 over the period. It's 1 over 4 because t equals 4 seconds. So my answer is frequency is 0.25 over seconds, or just 0.25 hertz. Okay, so this one, they give me the, okay, this is the same thing. I should just skip it. So the period is 2 seconds. What is the frequency? Frequency is 1 over t. Was 1 over 2 is 0.5 hertz, or cycles per second. This one confuses people sometimes needlessly. If you understand what the definition of period and frequency are. So I think it's easier to do frequency here first and then find period. So frequency, frequency is the cycles per second per time. So how many cycles? I got 40 complete cycles in 8 seconds. So I'm getting 4 hertz or cycles per second. The period would therefore equal 1 over f is 1 over 5 equals 0.20 seconds. Super easy. Frequency, period. So t equals 1 over f equals 1 over 8, whatever that is. Seconds, 1/8 of a second, looks like that's 0.125 seconds. So I'm going to round up. The 5 makes the 2 go up. Forgot to push the record button as I was working this. Okay, so an oscillation is a cycle. You do 20 cycles in 5 seconds. Okay, so first I can find the frequency. So frequency is cycles per second. So that's 20 cycles in 5 seconds. That comes out to 4 hertz. Then to find the period, that's what I'm looking for, capital T, I invert the frequency. So 1/4 is 0.25 seconds. This is way back here. I believe I already talked about this on the first, probably 3rd page. Okay, so let me just be sure that you understand that this is the equilibrium position. So how many amplitudes does it travel here? Okay, so from here, from here to there is 1 amplitude. Okay, and then from there to there is another amplitude. And then from there back to here is another amplitude. And then as it moves from there back to there is another amplitude. So add these up, I got 4 amplitudes is 1 cycle. So 1 cycle has been performed, 1 oscillation, 1 back and forth. Now also notice what's happening to the force. The force is maximum at when you have delta, when A is delta max. The force is maximum, but it's 0 at the equilibrium position. So it continuously is going from maximum to 0, back to maximum, back to 0, back to maximum on the other side, etc. And okay, so they're showing that amplitudes, when you're extended, the amplitude is positive, and when you're compressed, the amplitude is negative on that side. Not that it doesn't really matter to me, but that's because F equals negative K delta X. So F, the restoring force F in the displacement, because that negative on this side are always in opposite directions. So here, right there, is the delta X max. Well, X equals 0 here. Right here, from the rest position to where the black is, that's delta X max as well. But that's negative, because from equilibrium position to the maximum stretched up. The maximum distance from equilibrium position, that's in the negative direction. Okay, but do notice that force, the direction of the force and the direction of the A are always opposites. Okay, that's kind of a picky little thing. Boom. Let's do some problems. Okay, the period is 2 seconds. Amplitude is 4 meters. That's delta x max. How far does mass travel in 4 seconds? So what you got to do is how many cycles happens in 4 seconds? Well, if the period is 2 seconds, 1 cycle happens in 2 seconds. And that's the frequency. That stays constant. Frequency isn't changing. Okay, the amplitude is. Okay, so we can make a ratio. How many cycles happen when you do 4 seconds? So, I mean, it's just a ratio thing. I could do dimensional analysis. So 4 cross multiply, 4 times 1 equals 2 times question mark. So the question mark is 2 cycles. So how far does the mass travel in 4 seconds? Well, that's like saying how far does the mass travel in 2 cycles? Well, every cycle you travel 4 amplitudes. So my answer would be 8 amplitudes back and forth. Okay, since this is a review, I'll probably not ask it again because, except for a semester exam, what is the spring force? That's F, the elastic, the restoring force. Spring constant of 100, okay, 100 times delta x, 10 centimeters, but I gotta change that to meters. So the 100 changes it back. So to 10 newtons, and it's always going to be in the opposite direction of what delta x is. Okay, so force, if the delta x is negative, the force will be positive. Okay, I'm going to add a table that I started on, like the second page right here. Okay, so I just added this table, and this is from the second page of the study guide, but I added speed because if the kinetic energy is maximum, kinetic energy is mv squared over 2, so the speed would be maximum, where the kinetic energy is maximum. The kinetic energy is 0 at the amplitudes because the object had to stop to turn around. Now the acceleration is the elastic force, which should be the net force for our problems. So the elastic force is m times a. So the bigger the elastic force, the bigger the acceleration. So where's the elastic force the greatest? At the amplitudes. So right, we already explained that. And so the acceleration would be 0 at the equilibrium position. Okay, that's kind of a tricky one, but you should learn these. To find what the acceleration is at any point, you do force equals k. I'm just going to disregard the negative right now because that's just a direction thing. It doesn't change of value also equals ma, because it's a net force. So A would simply equal the K times the delta X over M. Okay, so I'll put that equation in the equation sheet. That's how you can find the acceleration of a mass on a spring. Okay, the acceleration is in the same direction as the net force. All right, we should know that already. So, elastic force equal ma. These two guys have the same direction. And what else has the same direction? So the acceleration and the force had the same direction. If the acceleration is, if the net force, making this case, there's the equilibrium position. Right here, the dotted line. If the net force is restoring it to the right, the acceleration is to the right as well. And just to remind you, the delta x from the rest position, delta x is in the opposite direction of the force always, because F equals K delta x. That negative is not for the K, it's for the delta x. K is always positive. So whatever sign F has, that's opposite sign what delta x has, as you can see in this picture. That's why I put a negative on the A, because it's pointing towards the left. Okay, the sign of the velocity is always the direction that the block is moving. So in this case, it's moving to the right. Now, there's no real pattern you memorize for comparing the direction of the velocity and the direction of the acceleration. You already know that one. If the object is slowing down, V and A have opposite signs. If the object is speeding up, V and A have the same signs. Okay, so you remember this from dynamics, I hope. Okay, this has all been talked about before. You should take some time and reason it out. Okay? The displacement is from rest position to where your position is. That's a positive amplitude, positive delta x. Again, this is the equilibrium position. X equals 0 for that. Okay, F and A are always in opposite direction. F and delta x are always in opposite directions. In this case, the force is negative, and the delta x is positive. V is 0, but the acceleration is in the same direction of the force. So the acceleration would be to the left. Okay, velocity is negative because it's moving towards the left at this point. All this is showing is that here is a relaxed spring, no force. But there's no restoring force because it's not stretched out or compressed. But if you put a weight onto it, a mass onto it, and it stretches it out some distance, delta x, let's cross this out here. If you do that, delta x is this way. The the weight you're hanging on has, and it's not moving back and forth. I just have it sitting there. The weight is equal to, this is the weight. The weight of the block is equal to the restoring force because the object's just sitting there. Okay, so if you read this problem, the period is 4 seconds. The amplitude is 0.5 meters. And how far does the mass travel? So I'm looking for the distance. Sorry. I'm looking for the distance as soon as I get the ink right on this stupid thing. So I realize that one cycle occurs in 4 seconds. Okay? I know one cycle is 4 amplitudes. In this problem, one amplitude is 0.5 meters. And so, let's see what happens. So I got meters per second. And then how far does it travel in a time of 4 seconds, which is crazy because it's the same as the period. So 4 seconds over here. Bring seconds up. Now, if it wasn't 4 seconds, you just put some other number. So basically, I'm doing what? The frequency times 4, because that's always going to be 4 amplitudes per cycle, times the amplitude, the actual length of the amplitude, times the time. So that should guide you in your dimensional analysis. That would be the distance that the object traveled going back and forth. 4 cycles. Okay, so you probably can think this out without doing dimensional analysis, or you could use this equation that I came up with. Now remember, the frequency is 1 over the period if they give me the period, like they did here. This one is, let's see, 0.5 times 4 is 2 meters. Okay, I guess I'm just going to use, I can show you with dimensional analysis, or I can use this equation that I made up. And so 1 over 4 times amplitude times 6 is 3 meters. Okay, in this problem, we got K, spring constant. We got the elastic force. How far is the mass from the equilibrium? So we're looking for delta X, not the amplitude, just delta X. So that's using F, Hooke's law. There's a negative, but that doesn't matter. So 30 equals 150 times delta X. Delta X equals 30 divided by 150. 1, 2, 3, 4, 5. That's 1/5 or 0.20 meters. Okay, here's the concept questions that you can answer from your knowledge of what you're supposed to learn from that chart that I gave you, Drew. Where is the force on mass maximum? F max. Well, F equals K delta X. It's where the delta X is maximum. So that's either at positive A or negative A. So it's choice D. Okay, this is the same kind of idea. Where's the force going to be minimum? So F equals K delta X, Hooke's law. Delta X is 0 at the equilibrium position. So F would have to be 0 there too. The equilibrium position where you're right on equilibrium position. You have no displacement from the equilibrium position. So it's point B. Okay, where is acceleration maximum? So what's the equation? F equals ma equals K delta X, disregard the negative. So A equals K delta X over M, which will be in your equation sheet. So A would be maximum when delta X is greatest. So again, at the amplitudes. Okay, same question, but the minimum. So when this equals 0, A equals 0, delta X equals 0, when you're at the equilibrium position. Okay, we know that the velocity is going to be 0 when the object stops. Where does the object stop when it's on a spring? It's going fastest in the middle, so it stops at the extreme positions, at the amplitude. So that would be where A is maximum, where delta X is maximum, and that would be at the amplitudes, letter D. Okay, so once again, when something's vibrating back and forth, it has potential energy. It could be gravitational if it's a pendulum, or elastic if it's an elastic object vibrating, and kinetic energy. So we've used these equations before. So mechanical energy is the sum of the total EP and KE at any given point. And we're assuming, when we're doing simple harmonic motion, we assume that there's no work due to friction. There isn't any of that. So these two, EP and K will be constantly changing, but the total EP plus KE at any given point will be the same. This is because no work is lost as friction. Actually, it is, but what this slide is showing is that when you're at the amplitudes, you have no kinetic energy. So mv squared over 2, because you have no speed at the end. You're stopping and turning around. So the total mechanical energy at the amplitudes is EPE, like we said on the second page. When you're at the equilibrium position, the total mechanical energy is equal to 1/2 is equal to KE, 1/2 mv squared, because you have no k delta x squared over 2. You have no displacement. You have no potential energy. So all your mechanical energy is locked into kinetic energy. This is at the equilibrium position. So ME remains a constant. If you don't have any KE, it's all spring potential energy. And if you don't have any spring potential energy because of your position at the equilibrium position, you have only kinetic energy. Okay, so I said this all before, but you're seeing it written a different way. So this is a good graph of, let's say, this is a delta x versus energy, mechanical energy graph, but really it's E and KE and how they change throughout the simple harmonic motion. Okay, this is only half a cycle because you went from one amplitude to another amplitude, but then you go back. Okay, so this one parabola shows half a cycle because we have two amplitudes showing. This one from 0.1, negative 0.1 to 0, and then from 0 to 0.1. Okay, the arrowhead is just showing the velocity. It really isn't showing the direction of the amplitudes. So let's erase them. Okay, anyway, you can see that if I didn't give you what the titles on these graphs were, you should be able to still figure out what they are. So this red line right here, that's mechanical energy. Mechanical energy staying constant. Okay, that's why it's horizontal. But the green line is kinetic energy is 0 at the amplitudes, but maximum at the equilibrium position, which is 0, delta x. And vice versa for the blue line, which is EPE. The EP is maximum at the two amplitudes, but 0 at the equilibrium position. So notice that these are mirror images of each other, these two, EP and KE. Also notice that whatever the EPE might be, the KE value, that value plus that value would have to equal the ME value, any point, any vertical line along this graph. Okay? So ME is constant. So they're talking about right here at the equilibrium position. No. Sorry. At the amplitudes. KE is 0, and you can check that out for yourself. but okay, so this is the same kind of idea. At the equilibrium position where delta x is 0, okay, this is delta x. ME stays constant. K is maximum at the equilibrium position, as you can see the green line right here. And the blue line, EP, is 0 at the equilibrium position. Okay, so at this stretched out maximum displacement, the EP is maximum. We're right there at the positive displacement. The blue line, and then the green line is 0. The green line is KE, and the total energy is again constant. So we'd have, okay, so where's the KE maximum? Well, K is maximum when the speed is maximum, right? And so where's the speed? The maximum at the equilibrium position, that'd be letter B. Okay, so this one, total energy is ME. So where's that maximum? It's maximum everywhere, not just at the amplitudes, not just at x equals 0, but everywhere. As long as it's vibrating. Where's the kinetic energy smallest? That would be 0. Is where the V is 0 and the speed is 0 is at the amplitudes, because you got to stop before you turn around. If we needed to find the speed at a certain point, and it was in between the equilibrium position and the maximum displacements, amplitudes, we'd have to use this equation. But it's not as bad as it seems. Okay, so if we have a delta x is not 0 and a v that's not 0, we can always go this equals either the total ME, or this equals the KE max, or this equals the EPE max. So that would equal, then you could figure out either the X or the V at any position. So this is a pretty cool trick. Okay, so this is a simple one. Okay, here's K, here's M. Okay, this is the maximum displacement, so that's A. So what's the maximum elastic potential energy? That's K times delta X max, or A squared over 2. Okay, so just plug in your values. 75, we don't need the mass. 0.05, right? You got to change that to meters by dividing by 100. Squared divided by 2. I'm going to get 0.094 joules. Okay, what is the total energy? So what's the mechanical energy? Well, it's either KE max or EPE max, whichever one's easier to use, or it's equal to KE plus EP at that given moment. So what do we have? We got the mass, we got the spring constant, we got the amplitude. So we're going to pick EPE max. So that equals KA squared over 2. Again, A is delta X, right? Max. I'm just going to do what they do with the A. So K is 200 times amplitude is 3 squared over 2. So 100 times 9 is 900 joules. What's the maximum velocity? So that would be at the equilibrium position. I'm just reminding you from the previous slide. Okay, it's the same info. K is that, and A is that. Well, because EPE max has equals KE max. So we already solved that in the last problem to be 900. And so that equals mv squared over 2. So 900 times 2 divided by the mass, and then square root that. The mass is 2, so these cancel out. So 3 times 3, 30 times 30, so this is 30. That's what V stands for. Equals. Again, here's the mass, here's the K. Spring is stretched from equilibrium. Okay, so that's my A, either plus or minus. What is the maximum KE? Well, again, KE max is equal to EPE max, because mechanical energy doesn't stay the same. And when you have KE max, you have 0 EPE. And when you have EPE max, you have 0 KE. But anyway, I told you that already. So, what do I have? So I can find this. So that'd be KA squared over 2 is equal, if that's A is maximum. Okay, that's what KE is. Oh, wait, I don't have to solve for V. I'm just solving for the kinetic energy max. So it equals EPE max. So that'd be 75 times A is 0.05, because you got to change distances to meters, divided by that squared. So you get 0.094 joules. 0.094. Now they're asking for the maximum speed. Okay, I already have KE max from the previous problem. So let's solve it. So, I forget, 7. So 0.094 joules is equal to mass 1.4 times the speed, that's what I'm looking for, over 2. So cross multiply, 2 times 0.094, divide through by 1.4, then square root it to get rid of the square on the V. So you get 0.37 meters per second. Okay, here is the equation for the period of a spring. That's why we put an S here. Period of spring is 2 pi square root of m over k. You know what all these letters mean already. Okay. Where's the 2 pi come in from? I can derive it from the wave, but we won't. The wave that's made by something vibrating. We'll talk about waves and sound next unit. Now, notice, okay, so this is a mass on a spring. Okay, here's the K, here's the M. I'm looking for the period, so period equals 2 pi M over K under the radical. So what am I looking for? Period. So it's 2 pi times the mass is 0.5 divided by 120 under the radical. So when I do that, I'm going to get 0.41 seconds for the period. That's the time it takes to do one cycle. Okay, this one is asking the frequency. The frequency is 1 over the period. So basically find the period and invert it. So T equals 2 pi M over K. And if you want to, just invert that. 1 over T equals 1 over 2 pi over, times K over M. Okay, so either that or you can solve for the T and then invert it at the end. So what I have is 1 over 2 pi. It's probably easier to just solve for T and then invert that answer. Square root of 125 divided by 2. So I get 1.26 hertz cycles per second for the frequency. Same thing that I just recently did. So use that QR code and check your answer if you want. Then again, the frequency is 1 over T, so you take your answer from the previous slide and invert it. And so you can check your answer there. Okay, so here is the period of a pendulum equation boxed in black. That will be on your equation sheet. Notice that mass is not in this equation. It canceled out when I was deriving it. And so therefore, the mass of the pendulum doesn't affect the period. So what's the period of a pendulum? 2 pi L over G. G is the acceleration due to gravity. Okay, so that'd be 2 pi. 2 has to be in meters over 10, 9.8. Okay. I get 2.8 seconds. That's the period. So this is okay. So what is the frequency of a pendulum's vibration? Okay, the length is 2.6 near Earth's surface. So G is equal to 10. So I can find the frequency. Let's do it this way instead of inverting it. I can find the period, then I'll invert my answer to find the frequency instead of doing like I did last time. Okay, so this is 2 pi L over G. Okay, so it's 2 pi times 2.6 divided by 10. And what I get is, I get the period to be 3.2 seconds. Okay, so the frequency is 1 over the period. That's what they're asking for. The frequency is 1 over 3.2. So 1 divided by 3.2 comes out to be 0.31. And that'd be cycles per second or hertz. We can do the same thing that we did with the mass and spring with the energy, except energy is GPE instead of EPE. The potential energy is GPE. Same thing, except it's GPE, so it's MGH. ME is total. Okay. Let's do a problem. Where's the maximum gravitational potential energy? That's when it's at the amplitudes. By the way, the amplitude is this angle right here. Okay, so we won't be using that. Okay, the amplitude doesn't matter for the simple harmonic motion at all, for pendulums or for springs. I should have said that before. Okay. Here's the length of the pendulum. The mass doesn't matter. Okay. So they should have said the height over here from, they should have drawn a picture with the zero reference line or point, whatever. So that's what I'm looking for. That's H max. And here, H is 0 from the zero reference point, the lowest point in the arc. Okay, so what's the maximum GPE? I mean, I don't even have to. GPE is MGH. And so that'd be 0.5 times 10 times 0.08. Okay. So that'd be 0.8 times 0.5. Which is 0.40 meters or 40 centimeters. Wait. 0.40 joules. What am I doing? Because I just found the GPE. I have the height already. So that's 0.40 joules. And this one was the maximum kinetic energy. That'd be down here at the lowest point. So the maximum kinetic energy would be, right? But KE would be 0 here, and you'd have EPE. No, not EPE. GPE would be max, right at this highest amplitude. But K max, the GPE would be 0 at that point. So recall that ME equals KE max, or GPE max for pendulum, or KE plus GPE if you're not at the lowest position or the highest position. So K max equals GPE max, which we already found out. So K max equals GPE max, which we found out in the previous problem to be 0.40 joules. Okay, so we got mass here. We got the length here with the pendulum. Here's the maximum height. Where's the maximum speed? Okay, well, when you're at the maximum height, you can find GPE max. maximum speed would be from KE max. So I just look back and these are the same values in the last two problems. So this is 0.40. So maximum speed, KE equals mv squared over 2, where that's the maximum speed. So 0.40 equals 0.5 times v squared over 2. So 2 times 0.4 divided by 0.5. So 0.8 divided by 0.5. Take the square root of that. 0.8 divided by 0.5 is 1.6. Then take the square root of that. And that's 1.26. So at the bottom, that guy on the swing is going 1.26 meters per second. That's the fastest he'll be going on this pendulum. Please use the QR code there if you want to solve this one. It's very straightforward. Okay, once you find the period, you can find the frequency. Use the period of a pendulum equation to find that. So again, use that QR code to get the final answer. Okay, so let's look at the equation for a period. Period equals 2 pi. The equation for the period of a pendulum, L over G. Is the period affected by acceleration due to gravity? Yes, if you know the acceleration of gravity is low g right here on the bottom in the denominator. The length of the string, yes, it is. It's an equation. The mass of the pendulum bob, they call that thing at the end of the pendulum a bob for some reason. No, mass is not in there. So it's only 1 and 2. Mass is not in this equation. I could also say amplitude. Amplitude doesn't matter either. What is the total energy of 1 kilogram if its height as maximum amplitude is 0.20 meters? Okay, we did this already, so you can look at the QR code there. Okay, so you find a GPE max equals MGH, and you got all those values. And you might say, well, what's the KE then? Well, KE is 0, and you have GPE max, so the total energy equals GPE plus KE, but KE is 0 when GPE is max. Okay, we should definitely do this one. So a picture would have helped. Okay, at its amplitude is 1.5 meters above the equilibrium position. They should set, instead of equilibrium position, they said 0 reference line. So here's amplitude. When it's up there, it's 1.5. But I want to know when it's at the 0.75 mark, which is half that, when it's right there, where this would be 0.75, the height would be 0.75, let's call it H2. Okay, so the height is 0.75 at that mark. Okay, so what we have to do is in between the maximum height and 0 height. So we have to do this. ME is equal to, at this in between point, is equal to KE plus EPE at those points. Okay, so ME is going to be equal, I have information to find EP, is GPE, sorry, gravitational. I have information to find GPE max, because that's what ME equals. And so that'd be the KE at this position right here, plus the GPE at that position, which would be M times GH2 plus MV squared over 2 is equal to, okay, GPE max, let's do that right now. That's mg times the big height. So that'd be, I don't have m, but m's are going to cancel out anyway. So m times 10, that's what g is, times 1.5. So this equals 15 times m. Now you see m on all sides of the equation in every term, so you can cancel it out. So let's rewrite this. 15 equals v squared over 2 plus gh2. So don't cross multiply because the h is in the other. The 2 isn't in the second term, gh2. So let's plug in. 15 equals v squared over 2 plus 10 times h2 is 0.75. Okay, so now that's 7.5. So 15 minus 7.5 on both sides. This is kind of easy because it's only half of it. 7.5 equals v squared over 2. So v squared equals 7.5 times 2 is 15. So v, the square of 15. I meant the square root of 15. I said it wrong. And I'm getting 3.87 meters per second. So that's kind of tricky, I have to admit.